Well, hello and welcome to you. I just want to take a moment and thank you for your attention, for coming and doing your best in class. Today we're going to continue our conversation about the method of solving systems of equation we're calling elimination. The title of this is More Elimination. This graphic up here, right, shows a system of equations that's just set for elimination perfectly. And one of the things we talked about last week was the fact that we see that we've got this negative 3y and this positive 3y. When I add essentially 4 to both sides of the top equation, right? On one side I add 4 in the form of just the number 4. 17 plus 4 is 21. And on the other side, when I add something equivalent to 4, namely 2x plus 3y, I end up getting that 7x is 21. And you can see in that one very step, right, the variable y is eliminated, and we know that x itself has to be 3. And then now that we know that x is 3, we plug it into either one of the original two equations and we can solve for y. So that's the method kind of outlined. So we've learned how to use this method to solve systems of equations. In this method, we combine two equations in a way that eliminated one of the variables. This method is particularly useful for solving systems of equations where both equations are written in standard form. Today we're going to practice using the elimination method some more, and we are going to be writing some systems of equations from situations and then testing that. So as we work through these, I encourage you and any friend that you invite to work with you from home or in class to ask yourself these questions. How can we, or how can you, create one equation with only one variable? How can we eliminate one variable? And how do we know our solution is correct? So this first problem involves a birthday party, and Phoebe is helping her mom buy party favors for her little sister's birthday party guests. There were 11 friends that were going to be attending the party. Costume dragonfly wings cost $1, while fairy wings cost $2. Phoebe's mom spent $18 on the gifts. So when I see this, I immediately think, well, let's be real clear and write a let statement. So I'm going to say let's see, I'm going to go D. I'm going to let D equal the number of dragonfly wings. So this is one of, I think, 4 or 5 things I want you to get in your notes today. So let D equal the number of dragonfly wings, and also let's let F, not left F, let F equal the number of, you know her as Tinkerbell. Let's see, fairy wings. So if I was to, there's two equations described here. First of all, there's 11 friends attending the party, so I'm assuming that she's buying enough. It says 11 friends attending the party. I guess I could make the assumption she's going to buy 12, or she's going to buy extras. I don't know. I'm going to just go with the number that they said here, 11. So I'm going to say that if I were to add the dragonfly plus the fairy wings, I would get 11 items for the 11 friends. And then if I was to do so this is just the count equation, right? I've got some number of dragonfly wings plus some number of fairy wings that equals 11 sets. The other equation we have is the cost equation. So dragonfly wings cost $1, so I can say 1D plus, it's $2 for the fairy wings, so 2F, and mom spent $18. So this is one of those situations where we have a system that's really well suited for elimination. The only problem is that I need my variable, in this case D, I guess, to be opposites, and they're not. They're both positive. And if I was to combine these by adding equal things to equal things, I would get 2d plus 3f equals what, 29. And although that equation would be compatible with the system, meaning it would go through the exact same spot that these two equations go through, it would be better if I modified this. So I'm just going to take the top equation and I'm going to multiply every single element in this top equation by the number -1. It looks like I'm raising it to a power, but I'm not. I'm just multiplying it by the number -1. And when I do that, I'm going to get a -d minus f equals -11. And then below, I'm combining that with d plus 2f equals 18. So when we combine these things, if I add 18 to both sides, let's see, on this right-hand side, when I add 18, that's going to give me 7. Because I've got a -11 plus 18, that should give me 7. And on the other side, my d's are eliminated, right? D and -d is 0. And a -f and 2f is going to give me just f. So I can see f is 7. That was super easy. 7, 8, 9, 10, 11. That means that that d has to be 11. So I know that d plus f has to be 11. I'm sorry. D plus f has to be 11. Because f is 7, that means that d has to be the number 4. 7, 8, 9, 10, 11. Correct. So my answer is mom bought 7 fairy wing and 4 dragonfly wing sets for the party, if you will. Alright, so that's our first problem of the day. Let's move on to number 2. Rachel is trying to solve this system, and the first prompt A says combine these equations. So what happens? So let's go to Desmos real quick right here. Let's type both of these. So the first equation that you should write down is the 2x plus y is 10. And the second equation is 3x minus 2y equals 1. There we go. Now if I combine those equations, I do get the equation 5x, let's see, that's going to be a minus y equals 11. And the beautiful thing is I can see that all three of these equations are pointing to this solution 3, 4. However, when I combine those, notice that one of the variables was not eliminated, right? My x wasn't eliminated and my y wasn't eliminated. So I did get a third compatible equation with the system, but no elimination occurred. So for A, I would say elimination didn't happen. The next question is 2x plus y equal to 10? Well, yeah, and we can see that. Is 2x plus y equal to 10 the same or equivalent to 4x plus 2y equals 20? And we can clearly see that if I come up here. We've got this equation, and I want to see is that red one the same as 4x plus 2y equals 20? And I can see it is, right? These two equations, the top one, the one in red, right, and the one in purple, are clearly equivalent equations. And equivalent equations means they have all of the same solutions. So the line in purple and the line in red are equivalent to each other because they share all the same x, y values. That is, do they have the same solutions? Yes, they do. Are their graphs the same? Yes, they are. Justify, well, we graphed it in Desmos and we could see that they're all sharing the same points. So because this is an equivalent equation, can I use 4x plus 2y equals 20 instead of the top one? Well, absolutely I can. So what they're proposing here is instead of using this equation, right, we can modify it and write it as 4x plus 2y equals 20. And I can use that with the second equation, 3x minus 2y equals equals 1. So because this equation is equivalent to this equation, right? We can see in the graph that they share all the same solutions. And also, they're equivalent because we use the multiplication property of equality. We multiplied both sides of the equation by 2. So we are clearly getting an equivalent equation. Because those two equations are equivalent, I can swap out one for this one instead. And what's nice about that is when I combine these equations, I get that 7x is 21, therefore x is 3. So the difference is, after that modification, I can see that my variable y's were opposites of each other, and when I combined them, that variable eliminated. Now that I know what y is, we can go ahead and sub that in for, I guess, the top equation and figure out what x is. So we've got 2 times whatever x is plus y is 10. We know that x was 3. I'm plugging that in. So this becomes 6 plus y is 10, therefore y is the number 4. So our solution is the point where x is the number 3 and y is the number 4. So the question D says, why was the top equation changed? Well, it was changed. It didn't just change by itself. We changed it. And the reason why we changed it was we could see there was an opportunity to use elimination by multiplying this top equation through by the number 2. Right? I created a situation where I would have a positive 2y and a negative 2y. So this is the idea that I want to make sure we catch today. It's possible to use elimination even if one of our variables doesn't eliminate. We can modify the equation so that one of the variables will nicely eliminate. Let's go into our next example. Down on the farm, there are 21 animals on Farmer Cole's farm, all sheep and chicken. Okay, all sheep and chickens. So one of the things that I know this problem well, that I'm making the assumption that these sheep have not been in any accidents. They have all 4 of their legs, and that all of the chickens have not had any legs removed, or they're not strange mutant chickens that have 4 legs plus 2 wings, right? So if the animals have a total of 56 legs, okay, how many of each type of animal lives on his farm? Write a system of equations and use to solve it. Okay, so we're going to write that. And I'm going to start with my s. So I'm going to say let let s equal the number of sheep, and let c equal the number of chickens. That's great. Not their legs each, but how many sheep, how many chickens. So if the animals, let's see, there are 21 creatures that live on his farm, and they're all sheep and they're all chickens. No dogs, no cats. It doesn't say that. There's just 21 animals, and they're either sheep or they're chickens, which is a missed opportunity because I would want to have a dog perhaps that could help me with these sheep, but that's what it says. So if I add the number of sheep plus the number of chickens, right, I get that there are 21 animals. And if I make the assumptions I spoke about their legs, the sheep each have 4 legs, so 4 legs per each sheep. So if I've got 2 sheep, that's 8 legs from sheep. And the chickens each have 2 legs. So if I have 12 chickens, that's 24. For example, 24 legs from chickens. Turns out when I add those up, I get a total of 56 legs from the farm animals. So we are going to use the elimination method, and as I look at this, neither one of the variables will eliminate immediately. But I could make a modification like above, and I could actually do one of two things, right? I could either make it so that the S's would eliminate, the sheep would eliminate, or I could make it so the chickens would eliminate. I'm going to make it modifications so that the chickens eliminate. So I'm going to multiply this top equation by the number -2. And then I'm just going to rewrite this system. So this top equation is going to become -2s minus 2c equals 40, not positive, equals -42. So if I have equal things and I multiply all terms on both sides by equal things, I get equal things. So I just multiplied everything by -2. And that bottom equation is 4s plus 2c equals 56. That's just a rewriting of it. And I can see clearly that the chickens are going to eliminate here. So this equation is going to become positive 2s equals, subtraction time. I know what that is. It's 56 minus 42. And yeah, I did just type that into a calculator and I got that that is positive 14. Therefore, the number of sheep is 7. I have 7 sheep. If I put that into the top equation, the number of sheep I have plus c is 21. That's the top equation. I just found that the sheep was 7, and if I take that away from both sides, I get that I should have exactly 14 chickens. So the number of chickens is 14. So two things, right? I should write this down. Number of chickens is 14, and the number of sheep, wonderful sheep, you can get sweaters from sheep. That's why they're so precious. You get woolly sweaters from sheep. And chickens, you can get eggs. Not hard boiled, but you could hard boil them. So just as a quick check, I know that if I add those two numbers up, I should get 21 according to my system. And yes, 14 plus 7 is still 21. It hasn't changed. And the other thing is if I take 4 times the number of sheep, 4 times 7, I do get 28. And then if I take 2 times the number of chickens, right, I better, 2 times 14 is also 28. And if I add 28 plus 28, I get, well, that's nice. There's 28 each. Every single sheep gets a chicken. Or each chicken has its own sheep. All right, so that's the end of that. Let's move on. Okay, it looks like this will probably be the last problem that we do together in our notes. And just a cautionary tale, these can be a little intimidating. So let's try to think through these details. So while Brendan is vacationing with his family at the cabin, they take a motorboat on the river. The motorboat travels 18 miles per hour in still water. So if they were in a pond, right, with no current, no flow, it could go 18 miles per hour. Okay. So it says let W represent the speed of the river current in miles per hour. That's not the speed of the boat. That's the speed of the river current in miles per hour. So let's kind of at least highlight that let statement. Let W represent the speed of the river current in miles per hour. Write an expression for how fast the motorboat is able to go downstream with the current. Write another expression for how fast the motorboat is able to go upstream against the current. Okay, so we've got two things that we've been tasked with. This is a problem. I'm hearing, because they've given me these rates of miles per hour, I'm hearing distance, rate, and time. So I'm going to go ahead and start writing a table of values, or just to organize my work. I'm going to have a distance, I believe. I think I'm going to have a rate, and I'm going to have a time. And I'm going to write this as, I'm going to say this is with the river and against or upstream. Oh, let's just do that. We'll do downstream and upstream. So downstream, and that's when you're going with it, and then upstream. upstream. So that's when you're going against the river. So, when you see boats that are taking people fishing on the Sacramento River, you'll see the boats going upstream or downstream. When you're going downstream, right, the river's, you're flowing with it and you're able to move faster. And then when you turn the boat around and you're heading back up, right, towards Keswick Dam, upstream, um, when you're going upstream, it's pushing against you and you're going slower. So if I'm going downstream, my rate would be downstream would be 18 plus the W, right? Because it's increasing my speed because I'm going downstream. And if I'm flipping around and going against it, it's going to be 18 minus W. So now the stream is pushing against me. So I've got these two expressions right here. Okay, so now the problem says the motorboat travels 49 miles upstream, okay, in the same time it takes to travel 77 miles. Okay, so it travels 49 miles upstream. So down here, it travels a distance of 49 miles in the same amount of time it takes to travel 77 miles. Now, the other thing that we know is it says in the same amount of time, right? So because the time is the same amount of time, I can go ahead and place t into these two boxes and just say it's the same amount of time, and I'm just going to let t be that same amount of time. So let t be the time that it takes for it to go 77 miles downstream, and that t is the same as the 49 miles going upstream. So if I want to write a system, right, we've talked about the relationship between these two. If I take a distance, like say 5 miles, and I multiply it by a rate, like some rate of some number of miles per hour, right, when I multiply those, my miles are eliminated. Distance, rate, miles per hour, distance, 70, distance, oh, my bad. The distance is equal to a rate. Okay, that's what I keep writing, rate. Let's say I've got miles per hour times a certain number of hours. There we go. Now my hours will eliminate, and it's going to clearly just be a distance. So here's my system. I can write that 77 equals 18 plus W times T. Okay, and I can also write that 49 equals 18 minus W, also times T. Well, this is interesting. Let's see. I think that what I want to do is, in order for me to solve this system, I think I'm going to distribute the t to these two expressions, the 18 plus w and the 18 minus w. So if I do that for the top equation, it's going to become 77 equals 18t plus wt, okay, and the other one is going to become 49 equals 18t minus wt. So this is interesting, a little scary, a little apprehensive, but it appears, right, that this is nice because this expression, I've got a positive wt and a negative wt, and if I combine this system, right, it looks like that expression wt and negative wt will eliminate. And when I do that, on the one side I've got 77 plus 49, which gives me 126, and on the other side I've got twice 18, or 18 plus 18, which is 36t. So this is good because I believe I've figured out what t is, right? 126 divided by 36, 126 over 36 is t, and that looks like t, the number of hours, is exactly 3.5 hours. Okay, so we've discovered how many hours it takes, and I'm sure that that's not what they were asking. Let's see. Um, oh, it says, could you have used, use the system, use, what is the current speed? Oh, what is the speed of the current W? So they're asking me to figure out what W is, and I figured out what T was. So again, I could use either one of my systems here. I'll use the top one. I'll say that 77 equals 18 plus W times 3.5. So I'm just plugging in the 3.5 that I found for T in the top equation. If I take 77 and divide by 3.5, it gives me 22. So 22 is equal to 18 plus W. And then if I subtract 18 from that, I get that W is 4, right? So 4 is what W is. The current is 4. And again, this is not a problem where I'm feeling super confident right now, so I'm going to do the same thing with the second equation just as a check. I'll say 49 is equal to 18 minus W, and I'm going to put the 3.5 there as well. So now I'm just taking, again, the same value of T, and I'm plugging it into the second equation. So I don't know why I put parentheses there. So if I've got the 49 divided by 3.5, it gives me a beautiful 14. 14 equals 18 minus W. If I subtract 18 from both sides, right, 14 minus 18 gives me negative 4. Okay. So negative 4 is negative W. Therefore, W is still 4. So I'm much more satisfied with the solution now. I believe that in both cases the current, the speed of the current is 4, and these were expressed in miles per hour. The other question here, it says, could you have used the equal values method or the substitution method to solve? Explain. You do not actually need to use these two methods. Well, I think I could have, right? I think there's no reason why I couldn't have gotten T alone in this equation. In both equations, I could have gotten T alone by dividing by W, or 18 plus W and 18 minus W, and I could have set those equal. So I think that's probably fair game. So, all right, so that's it. So the last thing I want you to do is I want you to do these 3 problems, and it says for each system below, I want you to determine is the system a good candidate for elimination method, why or why not? What is the best way to get one equation with one variable? Carry out your plan and solve the system for both variables. Is your solution correct? Just take the values you get and plug them into the original equation to check. So do make sure you check. So these 3 systems are the ones that I want you to solve. And because you're being asked to verify that your answer is correct, I'm not going to put the solutions on the screen. So realize for A, when you get M and N, or for part B, when you get A and B, or for part C, when you get X and Y, make sure you plug in your variables into both equations and make sure that your solution does indeed act as a solution. It has to make both of the equations true. All right, so we're about almost 30 minutes. It's 28 and some change. Thank you for your attention. Thank you for taking good notes, and good luck with these 3 problems. And then of course we're doing the review preview this evening. I look forward to seeing you tomorrow and seeing you in class. This is Mr. Roberts. Have a good day.